Okay, yeah, good to see you again here. So far we have finished up to the chapter 3 and we started chapter 4. You submitted homework on chapter 3 last Thursday, and I started to grade those problems that you have solved and submitted. Okay, most of you have done very well on problems in chapter 3, and now I expect you to do the same thing on chapter 4 and chapter 2. We will have a first midterm exam on first 4 chapters of our textbook as soon as we finish up the chapter 4 and chapter 2. Okay, I have uploaded most of the lecture materials and lecture note and live lectures on chapter 3, 4, and 2. I have also added some other reading materials, and also in addition to that, I uploaded some lectures of Gilbert Strang at MIT, and his lectures were saved, and you can use his lectures on the materials that we are studying these days. One good feature of this is you can use the captions.
Okay.
So you can
Lecture 6.
not only hear his lectures,
And
also you can follow his lines of his lecture. He's a very popular math professor at MIT. Okay, I hope he can help your work on the theory of matrix. I also uploaded my own lectures on main theorems of our lecture, that you can use it, and also you can recall some of the main theorems that you have studied in the introductory linear algebra class, which you took when you were a freshman or sophomore. Okay, there are main theorems and the full detail of the proofs that you can easily recall. Those facts that you're supposed to know. And this is one of this is one way of proof the rank nullity theorem for the Macy, as a matrix version. The proof that I gave in a live lecture, it is a version for the linear transformation. Okay. And also it has a full details of the most of proof. And for this theorem, theorem 7.4.9, I have uploaded the full detail of the proof on this theorem with some more equivalent statements on this theorem. In this theorem, you will see the sum of the problems on this in your midterm exam to prove the equivalence of some of those for n by n square matrix for the non-singularity. Okay, and this is a problem. This is a proof, the theorem for the projections, and the Gram-Schmidt also normalization process, the proof, and if and only if statement for the diagonalization, all details, and also the different eigenvalues and corresponding eigenvectors, and some on the quadratic forms and some Hermitian matrices, and unitarily similarity and unitarily diagonalizable. And I think the very last one is a Schur's theorem that you should know. You should know. And those are the main theorems. Those are the theorems that you're supposed to know, and the theorems that you are learning here is the advanced version or different version and consequence of those previous theorems that you're supposed to know and have learned. Okay. In other than that, I also added some leading materials, not only the modern mathematics and of Europe, and I also uploaded some of the materials that you better know on the modern mathematics of Korea and the United States. That will affect you more than any other knowledge on the history of mathematics. Okay, and and also this is the section 3.9, the applications on vector spaces, and here you will find the interpolation and Wronskians, which was covered in section 3.9 in Korean. It will be much easier to just go through what is in there and how your knowledge on the previous sections can be applied for the real problems of the world. Okay. So yeah, you can just go. You can go easily on the application section in chapter 3. Next, okay, here, and you must have seen my lecture note on chapter 4 on linear transformation, and also, yeah, we have briefly took a look on chapter 4 last week, and the live lecture on chapter 4 was also given in here, so you must have studied on chapter 4, and okay. The definition of linear transformation on vector space. Suppose V and W are vector space. I believe you shouldn't have any problem to go through those live lectures on chapter 4. And also this is the application of the content in chapter 4. The section 4.8 deals with dual spaces, which is the application of all other informations in chapter 4. And here, you can easily follow what was written in English with the examples. So it will help you how the previous basic theorems and proofs and examples can be improved to the more advanced theories. Okay, and I also added some leading materials here, and this shows the review of chapter 4 linear transformation after the whole lectures. Pre-initial. should be able to follow those on chapter 4 as well. What else? First lecture on chapter 4 here, and second lectures here, and review of chapter 4. And here are some more lectures for those what you have studied. Here, the MIT lectures on LUD composition, and lectures on column space and null spaces, and lectures on independence and basis and dimensions. And I think you should listen this one. Okay. Professor Gilverstrand has been popular because of this lecture.
Okay, here is lecture 10 in linear algebra. Two important things to do in this lecture.
Yeah.
One is to correct an error from lecture 9.
Space, null space,
so the blackboard with that awful error is still with us. And the second, the big thing to do is to tell you about the 4 subspaces that come with a matrix. We've seen 2 subspaces, the column space and the null space. There's 2 to go.
You should listen this.
Okay. First of all, and this is a great way to recap and correct the previous lecture. So you remember, I was just doing R3. I couldn't have taken a simpler example than R3. And I wrote down the standard basis. That's the standard basis. The basis, the obvious basis for the whole 3-dimensional space. And then I wanted to make the point that there was nothing special, nothing about that basis that another basis couldn't have. It could have linear independence. It could span a space. There's lots of other bases. So I started with these vectors 1, 1, 2 and 2, 2, 5, and those were independent. And then I said 3, 3, 7 wouldn't do, because 3, 3, 7 is the sum of those. So in my innocence, I put in 3, 3, 8. I figured probably if 3, 3, 7 is on the plane,
so I will give you a chance to go through this by yourself, and also you will be able to find some other information. I have made my content on all of this, so I will supply those to you as our lecture goes. And these 4 fundamental subspaces, that's what you should take a look. And I will ask some problems on this lecture in your first midterm examination. And there are some other lectures on orthogonal vectors and subspaces and linear transformation in their matrices. This is also this lecture deals with the matrix representation of linear transformation.
Okay, this is the lecture on linear transformation.
You can review.
Actually, linear algebra courses used to begin with this lecture. So you could say I'm beginning this course again by talking about linear transformations. So in a lot of courses, those come first before matrices. The idea of a linear transformation makes sense without a matrix, and physicists and some people like it better that way. They don't like coordinates. They don't want those numbers. They want...
I think you already know the matrix representation of linear transformation already well. You have learned it from elementary linear algebra, and the many exam problems has been given for the linear algebra midterm and final exams, and most of you got right answers on those. So you know these contents already. You can just go through it, his lectures, and you may find some other information. But basically, on those lectures, Those are what you already knows. Okay, what else? And change of basis also here. Yeah, you may try these lectures on linear no.
Okay, this is the lecture.
I think I got the long one here. I will revise it. Yeah, I intended to upload it on lecture 31, not 30. So yeah, I will I'll make change on this. And you should have the lecture on change of basis. Basically, change of basis is another version of matrix diagonalization. So that was also well covered in elementary linear algebra course. And today, we will finish up the chapter 4, and then we will start the chapter 2 on determinant. Determinant is a matrix function that satisfies these three properties, such as this. Determinant is a matrix function on the set of matrices to the scalar field that satisfies these three properties: first, second, and third. The value of the function on the identity matrix is 1, and the value of the function changes sign if any two laws are interchanged. And also, this function is linear in the first law, where these Ri's denotes the law vectors, like this. Determinant is a function that satisfies these three properties. Okay, this is we can easily check f is a linear function, and we can also show the existence and uniqueness of those functions. That function that we defined the determinant. Okay, so we can draw the theorems on the determinant. That's what you have seen from your high school years. You already have learned most of the things on the determinant of 2x2 matrices when you are a high school student. And you have learned most of the facts and the theorems on the determinant for the 3x3 size matrices and 4x4 matrices. Here, in the matrix theory class, we expand all those knowledge to the n-dimensional vector space and n by n vector space of arbitrarily large size. Okay? And all those facts can be expanded to the n by n matrices, and these theorems that you already know are also valid for arbitrary n by n size matrices. And these are the things that you will see in chapter 2. Okay, and here I gave a lectures on the determinant. 1 and 2.
I know you have been busy to taking
Okay, those two lectures on the determinant will cover the most of the knowledges on chapter 2, and also I gave a review on chapter 2, and I also added some reading materials. And this is a sample examination that we had last year. This was the midterm examination of the previous year, and you will see what you're supposed to get prepared. Okay, And this is the theorem that you already saw in the elementary matrix theory textbook that I just showed on the main theorems of linear algebra. And those are the things that you're supposed to, you will see in the first midterm examination. Okay? I think that's what we're going to treat today. And there are some others. Okay. Any questions? Then we will talk those materials in detail.